Welcome to The Explainer. We're jumping right into a massive, often misunderstood buzzword today: machine learning. My goal here is to completely demystify this concept for you. We're going to cut right through the hype, use facts directly from our source material, and show you exactly how this works, what it actually does, and why it totally matters to you.
Okay, let's dive into this. Here's our roadmap for today. We'll define what machine learning is, how machines actually learn, explore the 4 types of learning, look at some real-world applications, touch on the programming languages, and then weigh the pros and cons. Let's get to it.
Section 1. What is machine learning?
At its absolute core, machine learning is the science of enabling computers to learn without being explicitly programmed. Think about it like this. If traditional programming is basically just automation, machine learning, well, it's automating the process of automation itself. We just don't have enough developers on the planet to explicitly code rules for the incredibly complex modern problems we face. So, machine learning solves this massive bottleneck by basically letting the data do all the heavy lifting.
And this creates a profound paradigm shift. Look at the traditional programming flow. You input your data and a program into a computer, and boom, it produces an output. Pretty standard, right? But with machine learning, you literally flip the script. You feed the computer the data and your desired output, and the computer actually generates the program. It literally writes the rules for you.
To bring all this complex math down to earth, our source material uses this brilliant analogy. It says, machine learning is like farming or gardening. Seeds is the algorithms, nutrients is the data, the gardener is you, and plants is the programs. I absolutely love this because it perfectly captures how organic the whole process is. The quality of what grows depends entirely on the nutrients, the data that you feed it. Section 2. How machines actually learn. So, to understand how machines adapt to new data, you have to realize it all starts with your training data. The machine extracts features to train an initial model. But the real magic? That happens in the testing loop. It tests the model, scores it, and continuously improves it. Every single iterative pass it makes through the data makes the model sharper, smarter, and way more accurate.
Breaking that down into a formal architecture, it takes 6 crucial steps. First, determine the problem. Second, collect training data. Third, select your model. Fourth, prepare the data. Fifth, test the system. And sixth, which is arguably the most critical step, validate and continuously improve the model iteratively.
Section 3. The 4 types of learning. Now, if we zoom out for a second, the machine learning universe operates on this massive mind map made up of 3 core branches. You've got supervised, unsupervised, and reinforcement learning, along with their hybrids. Let's actually define these individually so you can see exactly how they differ out there in practice.
First up is supervised learning. Here, algorithms are trained using labeled examples where the desired outcome is already known. Basically, you give it the answers up front so it can learn the pattern. This is primarily used for predicting future events based on historical data. A really great example of this is a bank feeding an algorithm years of transaction history so it can anticipate and flag fraudulent credit card transactions.
Next up, we have unsupervised learning. And this is exactly what it sounds like. The system analyzes data with absolutely no historical labels. It is not given the right answer to look for. Instead, its job is to independently identify hidden patterns and structures buried within the data. This is absolutely perfect for businesses looking to identify completely new customer segments with similar attributes for targeted marketing campaigns. Then we have a pretty clever hybrid, semi-supervised learning. This uses a very small set of labeled data alongside a massive volume of unlabeled data. Now, why do this? Well, because manually labeling training data takes an incredible amount of time and money. Companies use this method to save on those high costs while still guiding the algorithm toward highly accurate predictions.
Finally, there's reinforcement learning. This type identifies actions that maximize rewards via trial and error. It relies on 3 core components: an agent, a set of actions, and an environment. The agent interacts with the environment and gets rewarded for good actions. Because it literally learns by doing, this type is heavily used in super complex tasks like robot navigation, autonomous vehicles, and gaming.
Section 4. Real-world machine learning.
These abstract algorithms power some incredibly diverse real-world services. In data security, they predict code variations to filter out 325,000 new malware files every single day. In financial trading, machines execute high-speed trades based on real-time market probabilities. In healthcare, algorithms have spotted 52% of breast cancers a full year before official diagnoses. And of course, that's not even mentioning the smart cars, search engines, and personalized marketing you use constantly.
Let's look at a specific corporate example here. Facebook Messenger acts as a massive experimental testing laboratory for chatbots. By opening up their platform, Facebook allows companies, everyone from massive corporations to tiny startups, to leverage machine learning chatbots to aid their customer service. It automates information delivery while actually retaining user engagement.
Another really cool example highlighted in our source is HubSpot. They actually acquired an AI firm to integrate machine learning directly into their systems for predictive lead scoring. They use natural language processing to identify trigger events in the market and score leads. This allows their sales teams to smarter target prospective clients based on hard data, not just a salesperson's intuition.
Section 5. Languages behind the machines.
When we look at the top programming languages used in this field, Python definitely stands out as the most popular and adaptable. It's ideal for general-purpose data mining. But the others serve highly specific purposes. R is designed for statistical computing. Java powers big data tools. MATLAB is deeply rooted in complex numerical computing. And Scala, C, and SQL all have specialized roles depending on the exact requirements of the architecture being built.
Section 6. The pros and cons.
To remain completely objective, we have to weigh the facts. The advantages here are simply immense. Machine learning offers true automation, continuous improvement, and the ability to process multidimensional data. However, the disadvantages are equally heavy. It requires massive data sets and incredibly high resource computing costs. But most importantly, it is highly susceptible to inherited errors. Think about it. If you trained an algorithm with a biased dataset, it sets off a chain of reaction of undetected errors that can take a really long time to notice and even longer to actually correct.
Which brings us to our conclusion. We've seen how machines automate automation. We've looked at the data, the iterations, and the extremely diverse real-world applications. So I want to leave you with this provocative question to ponder. How much of your daily routine is already being shaped by the invisible gardener of machine learning? Keep an eye out for it today, and thank you so much for joining me for this explainer. Keep questioning, keep learning, and I'll catch you next time.